Hello.
Snow building up or no?
Those are a little slippery.
All right, those that are online, go ahead and make sure and check in with the check-in module on week 3. We'll get started here in a couple minutes. Those that are here, go ahead and go to week 3 lab, submit your name. Did you already check in up here?
I'm not.
Okay.
I'm working on that.
That's all right. I'll make sure and keep it up here till you check in.
Thank you.
Okay, those just joining online, make sure and go to week 3 module, click on the check-in and post your name. Then go to, you're already on the podcast, and you should see an area to post questions or comments. You can do that if you want to. It's optional. You don't have to. I'll try to get to them before the session's over tonight. We'll get started here in about 1 minute. Thank you. All right, those just joining the screencast podcast, go ahead and go to week 3 module, click on the check-in, post your name, full name. All right, so we'll get started.
What were we supposed to do for lab?
Just post your name. All right, so this week we're going over OSI. We'll be doing a video, watching a video at the end for our lab on data packets, how data packets work. When you click on a link on a website, how does that process work? How do data packets flow on a network? We'll be watching that video and going over that's really professionally done video on data packets and how data packets flow. Talks about things like data IPgram, IP packets, payload, ping of death, proxy, firewall, different types of ports that are on a network like port 80, port 21, port 25, what those are all about. And so let's go and get started. Those are online. Hopefully you've checked in by now. If not, you can do so in a bit. Tasks this week as far as assignments, you have week 3, chapter 2 review questions, quiz also for chapter 3 or chapter 2. And then the lab tonight is a video we're going to watch on data flow packets. Let me get in here. Bum, bum, bum. And I'm going to bring up chapter 2 slides. All right. Well, that's up. Before I get going into that, I got a few announcements to make. A couple things on our course website, myrbc.org. There's been a couple or one job posting I want to go over. So myrbc.org. Hopefully you have that bookmarked by now. I will screen a little smaller to see it. Go to the jobs menu, view jobs. I already posted on social media when it was posted. It's for programmer analyst position here at Rock Valley. And it is open full time, starting wage $49,958 through $62,693. It's an intro programming position. So students are taking programming here on campus or graduated are more than welcome to apply. Goes through the process of qualifications, minimal qualifications, and then the link to apply here. So avail yourself to that. Also, Internet of Things, I'll make a plug for that. It's May will be here before we know it, and May is Summer 1, and we're offering a brand new course in Summer 1 called Internet of Things. I'll be teaching that, and basically the Internet of Things, I'll go to the website to show you. Which is, I forgot the facts here on it. I'll pull it up here so I won't get it incorrect. Talk about Internet of Things as far as what it means. Is connecting and controlling devices via the internet. It could be any type of sensor, any type of like your doorbell, video doorbell ringer. That's a good example. Everybody's familiar with those. To a Nest controller device you've heard of maybe or not that controls the temperature in your home. You control that to cameras you can control remotely. And so it's been around for decades. The first Internet of Things device actually was in the 70s, which was the first ATM. The first ATM, that's technically an online, everybody knows what that is, but it's an online connected device to where you can get transacted cash from your bank. Big businesses are already on it. Morgan Stanley, 75 billion IoT devices by 2020 is what they estimate. That's a lot. 7 devices per person alive at that time is what they're predicting. $60 trillion in investment. GE claims that investments in individual IoT devices would hit $60 trillion in the span of 15 years. Big businesses are also ahead of the curve. Last year, 2018, research conducted found 23% of big global enterprise businesses opted for more IoT solutions compared to 14% of small and medium size. And one of the big benefits, by the way, of IoT is inventory. If you have the correct Internet of Things devices in your warehouse, it'll automate 90% of your inventory processes. Now, some people might argue and say, well, that's going to replace people. It could in some situations, but it also could increase productivity where those people could be doing other types of jobs in that business. Dark side of IoT, because it's grown so quickly, security is an issue. And so companies are working on ways to secure IoT, make it more secure. Wearables is a huge IoT market. Worth $25 billion by 2019. That's this year. And wearables devices like fitness trackers, smartwatches, those are IoT devices. Internet connected clothing, from shoelaces to jackets to hats to earmuffs to gloves, where it can sense things like temperature, and it can turn on heat in a jacket or turn on heat in gloves. It can push out data when you're running to your doctor if you have an arrhythmia. It can cause emergency personnel to be contacted if you have other health things that happen by wearing these types of devices. And so in the home, what ends with it ends on this one by, it says estimated prediction. You'll see an inward shipping of 10.2 million types of devices, these wearable devices, by 2020, which is 140,000 units, only 140,000 units in 2013. So from 140,000 units in 2013 to 10.2 million 7 years later, that's a big jump. If that tells you anything. 53 billion smart home market. And this is not the future anymore. Everybody either has something already in your house or you're going to be getting one. They're fairly reasonable to buy, from cameras to thermostat like a Nest it talks about. Philips Hue controlling lighting. You can have every light in your house be controlled with Internet of Things, and it runs from your app on a phone. And for about $100, you can pretty much set up your whole house to remote in and control your lights to save on electric bills and things like that. Research, Philips Hue did research by a company named Xeon. They smart home automation market could grow to a staggering number of $53 billion by 2022. And then return on investment, companies already seen it. Smart driving, everybody's heard of automated driving, autonomous driving. IoT is part of that. Internet connected cars, smart cars. Gartner says by 2020, 250 million vehicles will be connected to the internet for improved in-vehicle services and automated driving. So no longer is it just Tesla that's doing this. Ford, Chrysler, Chevy, Nissan, Toyota, all these car manufacturers are developing some type of IoT within the vehicle, whether it be sensors to save you from getting in an accident, to staying in your lane, something. Google, it says, by the way, has already built a continuous testing automated driving, and they drive their automated autonomous driving car that they use for testing 10,000 miles per week, or cars, plural. So the adoption of IoT, and this is all leading up to careers in IoT, by the way, is the reason why we're offering this, because industry is pushing Internet of Things, and they're predicting 123 billion by 2021. 77% in 2018, industries were already connected, 55% of healthcare, and 54% of car manufacturers already. That's just 2018. Already have IoT in it. So you're going to go over 4 projects in May in summer 1. 4 complete projects, 1 per Saturday. It's a Saturday course. Check-in time will start at 7:30 to 8 a.m. And then from 8 o'clock till around 11:30, you will create one of each of these projects each Saturday. The first Saturday, we'll be creating a motion detection. And by the way, each week we'll have the devices and to make these will already be on site. I'm writing a grant for costs, so students won't have to pay for anything, even though they're really not that expensive. Each one of these only costs about $45. It's really inexpensive. But each one of these connection or Internet of Things projects have a couple components. One is, as you can see on the screen there, on the left side on that motion detection is a sensor, the motion sensor. Okay, that's an Arduino, which is a real popular. You might have heard of Arduino robots or whatever. Arduino is still the #1 provider for sensors. On the right is a photon device from a company called Particle. It's a Wi-Fi Pro photon device, and once you set it up, you can connect it to a rechargeable battery and just let it sit somewhere. And depending on the battery you have it connected to, it could sit there for months on end on that rechargeable battery and do motion sensing and send notifications to a text message or to a phone, a database, or whatever you want it to do. Second week, we'll be doing one called controlling a servo. And a servo, all it is a robotic arm where you can remote in to control it with your app, or in this case, it's a simple box picture frame that everybody's seen before. So instead of a family picture, it has different things to wear for outside or things to take outside, like an umbrella, a snow coat, t-shirt, snow coat and gloves, to a shovel. And depending upon the weather, every 15 minutes, the Internet of Things device will check a global free provider of the weather and will move the servo arm accordingly to wear what you need to wear or what you need to do before you go outside every 15 minutes. Mounts on the wall, just like any other picture, The battery on that lasts anywhere from 3 to 6 months, depending upon what type of batteries you get. That's the second project. Third project is wearables. The little circular device there could be utilized for earrings, shoes, buttons on jackets, a whole other different uses. This one, basically, once it's completed, you'll be able to control the lights on that sensor to any color, any spectrum of color you want with a mobile app. And the mobile app, it actually is just a web page. It's a web page pushed to Android or iOS, either one. You just tap your finger on the color you want it to be, and then that device could be at home, it could be in Alaska, and it would change to that color that you change it to. And then the last one's temperature reading. This week, a lot of concerns of busted pipes in your house, at work, for water. These type of sensors could be placed in areas like that and give notifications when it gets below a certain temperature. These are also used in dryers, where you could set it up easily to be a sensor for a dryer. When it reaches a certain temperature, it alerts you. Or refrigerator, list goes on different uses that you could use it for. And so 4 projects, 4 Saturdays: motion detection, first Saturday; second Saturday, controlling a servo; third Saturday, wearables; fourth Saturday, temperature reading. And so that's only 4 weeks. It's a 3-credit class. We're pushing it out in other venues, but I'm trying to get our students to kind of make a mental note of it now, because I'm guessing when the registration opens for this, it'll fill up pretty quick. I can only fit in there 19 students. That's all I can fit. So more than likely it'll fill up pretty quickly, because I've been asked to teach this the last 4 or 5 years and just haven't had time to do it. So it's a good time to do it. As you can see with the market the way it is, the need for people that know how to program stuff like this. And by the way, you will be programming, even if you're not a programmer. Each project, you will learn a certain type of program. Like each one of these has a program language called Python, which you will learn how to control these devices with Python through a web interface and push data or push a code to that photon device that I mentioned, which is actually this one right here, the little device there on the right. Questions on that? So that's the Internet of Things. That's coming in May. And then the job posting, if you've not yet bookmarked the mycis, myrbc.org, do so. And then also follow us on Facebook and Twitter. One last announcement I want to make is in October, I put in for a $30,000 grant along with some other folks here on campus, because I teach, have since 2015, a workshop called Learning Coding with Robots, okay, using a little robot called the Ozobot. The cost of the workshop, I'm only charged as the cost of the robot. I'm charged for the training or curriculum or anything like that. So long story short, it was awarded. We were awarded that grant from Northern Illinois, Community Foundation of Northern Illinois. RBC was awarded a grant of $30,000 for teaching the Ozobot workshops. That translates to 600 kids, 600 youth from K to 8 that can now can have the opportunity to not only take the workshop, but take the robot home. So we're looking at-risk youth, as well as schools who maybe don't have a computer lab and can't offer something like this, be able to go in there and offer it to their students. And one of the benefits of it, besides taking the robot home after the 2-hour session, is I've created a website that's in tandem with it that I created a while back with the objective was to give attendees more to learn when they go home. And so I'll show you what that looks like. So here's the Ozobot website that has in it everything from the binder that we use to individual little labs. And I'll show one quick This is a quick video. This is actually of a or picture of some students doing some work with a lab in Ozilbot. It's fifth grader in California teaching Ozilbot to other fifth graders in South Korea.
Such energy with them. And the thing that I liked was that South Korea was showing us things that they were doing and asking questions, and my class was like the little experts, and they could show them, and then it kind of flipped. And South Korea was saying, hey, we figured this out. My class was like, oh my gosh, that's so cool.
If you put certain colors like this in a row, it will make the Ozilbot do different things.
The passion behind just that little bot kind of transcended all the way over to South Korea, and their passion transcended all the way over here to California, and we were able to communicate with
We can follow
them,
lines of
collaborate
drawing,
right over
and you can also program it both.
and creativity.
So line
was
following
happening. My
robot
kids didn't
and
want to go home,
programming both.
but they needed to, and South Korea didn't want to stop because they're just starting their day, but they had to.
Okay, I think we're ready to learn about the app.
Another black line after that, and then it should be able to do the code that you want, whatever it says you put. It was flashing for you because it was on flash mode. If you tap on it, it turns to static mode.
Thank you. I think Ozilbots is a great introduction to coding for students, especially young
Anyway,
students. That are
that's a little bit of it. Tons of videos we put together for it, even personal ones. So anyway, that's pretty exciting. $30,000 grant. That's going to reach a lot of kids. So I'm pretty excited about doing that. One of the ways we're going to reach these kids is we're working on, it doesn't mention this in the article, but we're working on a tech bus for the campus to where we'll be able to drive around the community in a huge bus and pull up to middle schools and to events with things like the Ozilbot. And kids can load into the bus. So even if they don't have a computer lab in the school, they can have a makeshift computer lab, a mobile computer lab in that tech bus for them to learn. So that's pretty exciting. We're still raising funds for that. So that's a few announcements we got. And boom. Now let's jump to chapter 2. And we'll go over chapter 2, and then we'll go right into the video, which is a data flow video. It's a really fun, it's a cheesy video, but it's a fun video. It's a really cool video. It's professionally done on how data flows on the network. When you click on a link on a website, what happens. But we're going to talk tonight about different types of organizations, a part of networking, and OSI, what that's all about. All right. So one of the things when you're talking about networking is standards, whether it be for NIC cards, whether it be for Cat5 cable, whether fiber, Wi-Fi. You have to have standards because, as you can imagine, there's all these third-party companies creating hardware for everybody to use on a network. So you have to have some type of standards for things to talk correctly, right, on a network. So that's what basically network standards are all about. So it's an agreement that companies sign up for and sign up to when they create these products, whether it be 3Com or Cisco. And it basically stipulates design and performance of a particular product, like Wi-Fi, certain criteria for if you're going to make a Wi-Fi access point, here's your criteria you need to make that device work. Standards are essentially, in the networking world, wide variety, as you can imagine, from everything in your computer, hardware-wise. So you got your NIC card, you have your motherboard, you have your memory, you've got your hard drives, you've got your monitors, keyboard, mouse, all the peripherals that can connect to it. So a lot of different devices, cameras, scanners. It ensures basically its compatibility, that everything is connected to your computer or to your networks are compatible. And it gives you what's called a minimal standard. Like if you bought Office or Windows software operating system the last few years, you might have read on the software, minimal requirements of memory is, let's say, 8 gigs or something for Windows 10, whatever it might be. or 6 gigs or 4 gigs, whatever it might be. Now, minimal standards is actually that, minimal, meaning you can just get by. It's not optimal standards, but minimal standards. Because an example with Windows 10, if you install Windows 10 with 2 gigs of RAM or 4, I think 4 is what they ask for. 4 is a minimal. You're not going to be able to screen through the operating system with 4 gigs of RAM. It's going to go pretty slow, depending on, say, you start 4 applications, it's going to get pretty slow. And so servers have minimal standards, Wi-Fi access points have minimal standards, Cat5 cabling has minimal standards. Not ideal, it's minimal. Many organizations, when it comes to these standards, have different parts that they play. One of the big ones is ANSI and IEEE. These folks set wireless standards for all the wireless devices and communications. And then being a network professional yourself, you have some responsibility of being familiar. You don't have to be an expert, but be familiar with what these organizations do and how it benefits and impacts you as an employer or employee in the networking field. So ANSI is the first one we're going to go over, the American National Standards Institution. It's 1,000+ representatives of both quasi-industry, governmental, both. And the reason they have both is, as you can imagine, people in the government have no clue about technology, usually. You've seen the interviews with Mark Zuckerberg. You probably realized that recently when they try to explain to him what the internet was. That's not good. So, or what the email is. Then determining standards for electronic industry and other fields. It requests voluntary compliance in this area. And a lot of your devices, almost every device I can think of, I can't think of one that's not. If you buy any Wi-Fi device recently, it'll have a little sticker on there. One of them will be the ANSI certification sticker, right? It went through these folks. They got the stamp of approval anyway from these folks. It's rigorous testing. They take folks from this group to the company, or the company sends them the hardware. They go through the rigorous testing and then put their stamp of approval. Or you need to work on this or work on that, then you'll get it. All their documents are online, called white papers. So if you're bored one weekend and want to read a 1,000-page document on Wi-Fi WPA2 or something by the fireside, you might want to do that, which I know many of you won't. But it is something that you could do if you wanted to. EIA and TIA. The EIA is Electronic Industries Alliance. It's a trade organization, represents U.S. Representatives from U.S. electronics manufacturing firms are part of it. It sets standards for all its members, helps write ANSI standards, lobbies for favorable computer and electronic legislation. The TIA, the Telecommunication Industry Association, was formed in '88. The EIA subgroup merged with the former United States Telecommunication Suppliers Association. The focus of the TIA was the standards for information technology, wireless, satellite, fiber, and telephone equipment. It's also the guys and gals who do the cabling certification. So when we do the cabling lab here next week or week after, you'll see on the cable itself this standard. It'll actually say in black writing TIA EIA 568B certified. Guidelines for installing network cable, creating network cables and as you can imagine, there's many, like in the back of the room, if you look on the top there, those cabinets, a lot of different manufacturers that develop those cablings. So they just have to follow these guidelines and get the stamp of approval of the TIA, EIA. The IEEE, it is an awesome organization. Institute of Electronic and Electronics Engineers. Goal is promote development and education, electrical engineering, computer science, host symposiums, conferences, chapter meetings. They maintain a standard board, and they have a lot of technical papers and very highly respected. They do come here on campus, by the way, once a semester, because they have a student group, a student IEEE, which I recommend you getting a part of. It does cost a little bit, but you get a lot of benefits from it. You can go to conferences for free, all the local chapters meetings for free, which they generally feed you on all those. And then at the conferences, they do competitions, a lot of fun competitions. Everything from networking to programming. And there are a couple competitions in Chicago every year. So it's just fun. It's a fun all-around IT resource for you, because you get to meet a lot of people, network with a lot of people. Like a lot of people in the IEEE here in Rockford region are CEOs, CFOs, engineers, programming guys and gals. And if you go to these, you find out about jobs and stuff and things that are available, because that's where they hang out. They want to see all the new technology. IEEE usually launches somebody speak about a new product from a company at their meetings, and then all these people gather around and get to play with it. That's the kind of group it is. And so a lot of good shoulders to rub while you're in there, get connections and networking. And so it's represented, or ISO is represented by what's called the International Organization for Standardization. Never been there, but I'd like to go there. It's in Geneva, Switzerland. I've seen pictures of it. It's really beautiful. Well, Switzerland itself is beautiful, but they have 57 countries represented in this ISO organization. The goal is establishing global communication, free trade. So one of the things that Elon Musk is doing right now with his low orbiting satellites is to get free internet globally, broadband for the entire world. Also, there's a tier on that he's talking about. Next, the second project phase is for people to pay for a certain amount. But the first phase is to get free internet for everybody to have in parts of the world that have never had internet before, never had access. So ISO is behind that, by the way, and they're all for that, definitely. It's widespread authority, different from all different countries. The ITU, the International Telecommunication Union, specialized in the UN, they started in 47 because that's when the UN started back up in 47, became a nation. And they regulate developing countries to get technology like internet, broadband, satellite connectivity, things like that. Members of 191 countries. Focus of the ITU is worldwide internet implementation. They want worldwide. Again, they're behind backers of Musk, what he's doing, and a lot of folks from there are going to be working with him on that. And so, again, from remote parts of the world, third world countries, third world regions, tribes in Africa and all over the world, Sudan, getting internet in those poor, very poor areas of the world to where they can learn and grow and have opportunities maybe they otherwise wouldn't have. ISOC is Internet Society, founded in '92, a professional membership society establishing technical standards. Their growth or current concerns are internet growth, internet accessibility, information security, stable internet addressing. So you might have heard of version 6 internet, IP version 6. These are the folks that are we're behind that. And they're also behind open standards, to where something that works for whatever the standards are to come out, whatever hardware comes out, whatever technology comes out for internet, that it works for all devices and all operating systems. ISOC oversees groups with specific missions. There's 2 of them. The Internet Architecture Board. It's a technical group that oversees internet's design and management. And you might be asking, what do they have to manage? Well, they're managing not only the global growth of the internet, they're also managing part of their goals or part of their mandates is managing all the IP addresses all over the world. So when you get a website, if you're a company or an individual who gets a website, that's an IP address. It's yours and only yours. Nobody else can use it. So there's only so many numbers that can go around. So that they're over that type of management and design, of making it more numbers available. That's where version 6 came in. The IETF, Internet Engineering Task Force, sets internet system communication standards, protocols, and operation interaction. Anyone can submit proposals. Very elaborate review and testing in this group. And then IAN and ICANN, the IP, which you heard about already, we've talked about it, the Internet Protocol, addresses computers, internet, network IP addresses. And then IP addressing management, IANA, the Internet Assigned Numbers Authority, started in '97 with 3 registrars. They had the ARIN, the American Registry for Internet Numbers, the APNIC, which was the Asia Pacific Network Information Center, and then RIPE, RESU, IP Europeans. That was all in 97. Then in 90s, ICANN was formed. All three became ICANN, the Internet Corporation for Assigned Names and Numbers, a nonprofit corporation. It does have a 501c3 nonprofit status. And its job is to remain responsible for all IP address and management within the world. And IANI performs a system administration. Users and businesses obtain IP addresses from ISP, and they report to these folks to manage, to make sure the numbers, where the numbers are and where we're at with as far as how many numbers are left. So OSI, this is one of the things when you're taking any networking exam, you have to know what the OSI is, and it's these components here we'll talk about. It was formed in the 80s. It's just a model for troubleshooting in networking. And it's not tied to any physical, anything on a network, it's just a model. So you got 7 layers. You got physical, data link, network, transport, session, presentation, and application. It's a protocol only. It usually interacts with above and below layers. Like the application layer, it interacts with software, but it doesn't any particular software, just software in general. The physical layer interacts with cables and Cat5 NIC cards, things like that. It's theoretical, representing everything on the network between 2 nodes. And we'll look at an example here in a second. It's hardware and software independent. Every network is represented. Every network communication process is represented. And you'll see this in a video. One of the things it talks about is data packet flow, or PDUs, protocol data units, discrete amount of data on the application layer, and flows through levels 6, 5, 4, 3, 2, and 1. And the data units you'll see represented, I like to, represent like cabooses on a train. So if you send a data packet, if I'm sending one to you of an email, let's say it's a 5 meg packet. These units, these PDU units, might be split up into 1 million. We'll say more productive. We'll say more feasible here, 1,000. 1,000 little cabooses, that 5 meg packet will be split up into evenly across the network. 2 reasons for that. Once it's split up, it's easier to send it once it's split. So it starts out at 0 caboose and goes to 4,999. And each one of those cabooses are evenly distributed, that data. Okay. Now, what's nice about it is those cabooses can go all different places on the network. And then when you come back to your computer, it's smart enough to know, and the internet and the networking is smart enough to know, that it puts all those packets back together in the order they were sent for you to see that email. Okay. And so the flow is the OSI through all these different layers, all these 7 layers. And so here's what it looks like. So you've got, for instance, 2 computers talking to one another. We'll start with the left one, and we'll start with the sending. So physical computer on the left. Okay, it's going to go through the application layer first. We'll use Eagle as an example. You logged into Eagle tonight, right? Authenticated. Then what did you do once you logged in? What's the next thing you did when you logged in? Somebody tell me. When you logged into Eagle, what'd you do? Yeah, well, you're already there. You already logged in. You've already authenticated. What'd you do then? Yeah, you went to what, PCT110, right? Clicked on the icon, whatever. Then went to lab 3, then submitted your name. Those are all application layers, okay? Those are all application stuff. So when the application in this case is Chrome or whatever web browser you use, that's the application. So the application layer, RVC Eagle, you logged into, you did your stuff, you submitted your name, and then you hit submit. As soon as you hit submit, it goes from the application layer to the presentation layer. The presentation layer takes your data, which is now in analog form on your computer, and starts converting it to digital. It starts packaging it, first of all, saying, okay, what type of data is this? Well, is it an image? No. Is it a video? Nope. Is it a sound? No. What is it? It's text. It's just simple text, right? So it encapsulates your packet with a text encapsulation saying this packet text going to happen here in the presentation layer. It's going to notice immediately, stamp that packet with its a text encapsulation. If it's a video, it's stamped with the video. Audio, audio, so on and so forth. PDF, PDF. Then it goes from presentation layer to session layer. Session layer, its whole purpose is authentication and connectivity. So when you logged into Eagle, went to Lab 3, submit your name, before you could submit it, it had to check in this session layer, are you still logged in? What if you sat there for 20 minutes? Came back, then hit submit. It might go, you're logged out. You got to log back in, right? Because Eagle eventually is going to time out, right? That's what this section does, or this area does, this model session area. Then transport layer is getting ready now to put everything together. It's deciding, okay, what's your IP address? What's the IP address of Eagle's server that you're submitting it to? Okay, what's the time here? What's the time there? What's the data size here? What type of file is it? All that stuff's going to be encapsulated in this transport packet. Then the network packet starts gathering things like the network address of your network address on your computer, because every computer has its own network address. It also has still in that the source IP address, which is you, the destination IP address, which is Eagle's server, the data size, the data packet, the data type, all that stuff's in there still. Then finally, the data link. The data link now packages it all into a digital package to get ready to go through the physical layer, which is your NIC card, which goes out through the internet, through the network, at the bottom there, up to, we'll say, the Eagle server there on the right. The Eagle server, through the NIC card, data link layer, it sees that it's what type of packet it is, what your IP address is, what the data size is, what your network ID is, go through a network pack, transport packet, session packet determines it's still authenticated, presentation packet, it's now taking that data that you sent it, which is your name, and presents it to an application, which in this case, for argument's sake, is going to be a SQL web server, SQL database, we'll say, is where it's storing your name in a SQL database. For when I log into it tonight and I can see who was in there, I can see your name in that database when I log into that assignment for the lab. I go in and I grade it. I'm on the right side in the physical layer. I'm in Eagle grading. I hit submit, goes through my Eagle Chrome browser, logged into Eagle, sees it's in this case, a number, but it's a data type for a database. So really more of a text type of packet. Same thing as before, session packet, am I still connected? Transport packet, what type of data is it? Where's it going? Source, destination, network ID on my end while I'm logged into Eagle. Data link, okay, it's packaging it for digital link now. Physical, going through the Eagle server, back to your computer, reversing the logic all the way. When you get an email saying Lab 3 has been graded, and you click on it and voila, you see that information. And so that's all done through what's called the OSI model. Now, some companies will say we are a level 2 company or level 3 OSI company, meaning they focus only on data link and networking, which Cisco does, right? Cisco focuses on, that's their company. That's what they make money at, is the data link networking layer of the network, basically. So your switches, your hubs, routers, all that stuff is made in conjunction with Cisco. So the top layer, the application layer, is the 7th layer. No software applications, but works with software. Its function is to facilitate communication between the software and the lower level services in that OSI. It interprets the network request. Application interprets the data. In this case, we talked about text data. Software negotiates the application protocol, formatting, procedures, security, synchronization, The requirements, like I talked about on that capitalization, it'll do that. Then the presentation layer below that accepts the application layer data, formats it into understandable information for the host to get. So it might be a text encoding like we talked about for the name that you submitted. It now packages that and performs the compression needed. Presentation layer manages the data and encryption and decryption. Because as it goes through that bottom line, that should all be encrypted and not being able to be intercepted. Session layer is the next one. Protocol function here is to coordinate communication between two nodes. Its connection is for ongoing data exchange between two parties. It's constantly doing this. Are you connected? Are you connected? Are you connected? Are you connected? Who are you? Are you connected? Who are you? Are you connected? Who are you? That's all it does, all the time, constantly. It's connection between remote client access server, connection between Eagle and Eagle web server, as we gave the example earlier. Function and session layers to keep things alive, keep the connection alive. Because if you don't have a connection alive, right, if you're logged into Eagle, what's going to happen if you try to submit your name, if the connection's not alive? Is it going to let you do it? No. More than likely, it's going to do what? If it's not alive, it's going to ask you to do what? Again. Log in again, right? You've had that happen before. So maybe not with Eagle, maybe other things like a bank account or whatever. Eventually, it's going to session time out, right? Which it should. Synchronization also is constantly synchronizing. Are you there? Are you connected? Are you there? Are you connected? Okay, I'm connected. Are you there? Constantly doing that. Determining if communication has ended or to restart. Terminating communications. So when you log out of Eagle tonight, terminated. That's in the session layer. Then the transport layer. It accepts data from the session layer, manage end-to-end delivery. Here's where I talked about earlier, source IP, destination IP, data size, all that good stuff. It handles flow control, and it's connection-oriented, meaning it establishes connection before transmitting data. In there, it's got a thing called the checksum. The checksum basically is a way to make sure the file that you sent is a file that's received on this end. So in a checksum, it's going to have a number of factors. It can have the file, it's going to have the file name, size, source IP address, destination IP address, and then usually a unique code that should not change once it gets sent over. If a checksum changes from here to here, this place knows something's happened in between. There's been some type of interference or breaking of the data. It'll ask to resend it again, okay? All it does is ensure data integrity and that everything you sent is sent successfully. That way, when you send your name, it's not just the first 3 characters of your name and the last 2 are cut off. That would be good. So it sends everything, 100%. In the transport layer, has also connectionless protocols, does not establish connection with another node, makes no effort to make sure data is free of error. It's more efficient in connection-oriented protocol because it just makes sure that data gets there. That's all this part does of the protocol, the layer protocol. Then segmentation I talked about earlier, cabooses, that's the segmentation. It breaks apart your name. We'll say for argument's sake, if it's a 5-character name, it breaks it apart in five segments, 5 cabooses. Breaks it apart as it's going through the network. Then it comes back to Eagle server, puts it all back together in that segment in the order that it was sent. It also has on each caboose what's called an MTU, each segment, a maximum transmit unit that can be only 1,500 bytes. That is the cap. And so as you can imagine, if it's a 5 meg file, take 1,500 bytes divided by 5 meg to determine how many segments it needs to be split up into. It also discovers a routine used, this discovery routine to determine how many cabooses basically are needed in that segment. Then the reassembly that you'll see in the video in a bit is where it processes all those data units and puts it all together in the order they were sent. And again, they could be scattered in all different locations going across the network, hitting all different types of routers. But when it comes back to the destination, everything's put together in the order it was sent. And then sequencing is what allows that to happen. It identifies the segments belonging to that group and puts it together in the order it was sent. So here's an example. Sender and receiver, sender on the left, receiver on the right. The sender sends a long message, goes through the transport layer segmentation, through the network tunnel, comes back to the recipient and takes that message and those cabooses and puts it together in what's called the transport layer reassembly. It's where the user sees that message that you sent. And in my case, I see your name that you submitted tonight. Here's what it looks like in text, what it looks like in text. You'll notice at the top, a couple things we've already talked about. Port, source and destination. Port number 80, that's the internet port. Port 1958, sequence number, acknowledgement number. Source port, destination port, sequence number, acknowledgement number, header packet or header length. And then the flags show if that packet was acknowledged, if it was sent and completed, and the checksum, you'll notice it says correct in there, meaning the checksum that was sent was received with that same checksum. And this caboose only had 1,460 bytes out of the 1,500 allowed for that segment. Next is the network layer. Its protocols are to translate network layer into physical counterparts. So decide how to route data from your network ID to the Eagle server. Addressing, it figures out, okay, it's got a unique number that it gives you as a network in a device. Your NIC card is going to have a couple things. It's going to have an IP address, a MAC address, and the network address that this one's talking about. Types of addresses for nodes would be like network addressing and logical addressing. Packet information on a network layer, the transport layer appends the logical addresses like source and destination is on this. The routing, it determines immediately at this segment from point A to point B where it's going to go and how it's going to get there. Routing considerations before it does it is priorities, congestion, quality of service, cost of alternative routes. And then common protocols in this would be IP, and then fragmentation to transport those smaller cabooses across the network on the network layer. Here's what this packet looks like, or here's this protocol looks like. You notice at the top, instead of port numbers like the last one, it's IP addresses. So source address IP, destination address IP. Version 4 refers to the TCP version or the TCP version 4 or IPv4. Header, then it's got services field, length of data, flags, was it fragmented, not fragmented. Time to live, we'll talk about that when we do the ping lab next week. How long it lives on the network. This is 64 hops. TCP protocol, checksum was correct. And again, it repeats the source and destination IP on the network. Then the data link layer, we're almost there. Functions of this is divides the data that it received into distinct frames on the physical layer. And it structures those packages for moving the data into what's called a payload into the sender's receiver and receiver's address. Also puts in there error checking, controls, protocols, all within this frame package. Possible parts for communication mishap could be not all information is going to be received. You'll see that on the video in a second. For whatever reason, data packets fail. They don't get there. A server could or a switch could fail. It drops. What happens is it's just resent. It has to be resent again. So what's amazing is you could have, like, say, give the example I gave earlier, 5,000 cabooses, and 4,999 make it, but one doesn't. It knows that one didn't make it. It'll ask for that one to be resent again. Exactly which one to be resent again. Also in here is error checking. Could be things like I just mentioned. Frame check sequence, meaning there's maybe something was weird in the checksum, has to be sent again. And then also possible glut of communication requests. Too many requests could overflow the data network and could cause errors and ask to be resent again. Two data link sublayers within the data link are LLC and MAC. LLC is logical link sublayer on the network. And then you've heard of the MAC address layer, the sublayer of the MAC address. It's made up of, on your NIC card, 2 blocks. It's got a block D, which is a 6-character sequence, and it's unique to each vendor. So 3Com, Intel, whatever the vendor might be, D-Link. And then a device ID, which is a 6-character number added at factories at the vendor's factory, which again, putting together is a combined unique number. The MAC addresses frequently are depicted in hexadecimal, and then it can also be converted into ASCII code. And we'll be playing with MAC addresses quite a bit. In my 130 class, we do a MAC address spoofing lab. In here we don't, but we do talk more on MAC addresses. And when you do the NIC card installation, you'll physically see the MAC address on the NIC card. If you've never seen one, you'll see it in real time when you do that. So as you can see, the network layer at the top of the data link is comprised of the network ID from the network itself, network server. Then the bottom is the MAC address. Both of those are what's called a data link layer. So there's a picture of a NIC card, and then red is circled the MAC address. That's kind of like the VIN number on your vehicle or your social security number. It is unique and only one of a kind. Now we're getting to the physical layer. Physical layer, towards the end, the last layer of the physical layer of the OSI. It accepts the data link, generates signals and voltage, because in your Cat5 is a little small amount of voltage. Send that data, not enough to shock you, but there is voltage to send it. Copper transmission medium, that's part of the voltage in the middle, sends that signal across that copper wire. Fiber optics, another transmission medium, sends it through light pulses, through glass or plastic, whatever it's made of. And then wireless sends it through electromagnetic waves. I don't know if I mentioned this to you, but they have devices you can buy now, they have been for years, where because Ethernet does flow over a small amount of voltage, you can use the house wires or the electrical wires in your home or business to propagate your network. And so there's little boxes you plug in the wall, and you connect your Cat5 in that box. Then you plug the other box next to your router or your switch, whatever you have your source at home. It could be your Wi-Fi router from Comcast or whatever, or Xfinity. You plug in your box near that, and a plug-in Cat5 to your Xfinity cable modem port, and you've now connected that computer downstairs or upstairs to your network via hardwire through your house wiring over Ethernet, over wire. And so that way you're not running wireless, which maybe for that computer you need a stronger connection, a faster connection. This would be a way to do it, okay? Because wireless still isn't the same speeds as wired. And so if you need a wired, well, it might be an alternative, but you still have to run wires. You can use your house electrical wires to do it. It's not real common. People aren't really aware of that. So that's why I mentioned it this week. That way, if you ever need to do that and to save you running wires, you could use an appliance like that. And they sell those anywhere. Like Newegg is a good, you're not going to find them mainly at Best Buy. You have to go online to get them generally, like a Newegg or something like that. So physical layer responsibilities: detect and accept signals, pass data to the data link layer, set transmission rate, monitoring errors, devices operating on physical layer, hubs and repeaters. So on your table at the end, you'll see some switches. That would be considered physical layer. Your NIC card would be considered physical layer. And NICs operate both on the physical and the data link layer because remember, it's the protocol right above the OSI, right above that layer. So it falls on both. So this diagram just talks about the different layers and what all they do, from application layer all the way down to physical layer. We already went over. So the communication between two systems is you've got your data transformation, where the original software app differs from the application layer. Your PDUs, That's generated in the application layer. Your segments generates in the transport layer, or your cabooses, like I called them earlier. Packets generated in the network layer. It defines and logically assigns the packets with and addresses, source and destination. Frames generates in the data link layer, composed of several smaller components or fields. Encapsulation encapsulates each one of the cabooses with encapsulation of source as destination IP address, network ID, NIC, MAC address, things like that. So here is you'll see overlapping on all the layers. They can overlap above and below in that OSI model. Application header, presentation header, session header, transport header, all the way down to the physical layer. Frames on a network basically are taking your data and putting it in smaller fields to be across the network, go across the network. Ethernet, believe it or not, was developed by a company you maybe think of as printers, Xerox. Still very popular printer company. They developed 4 types of internet frames still used today. The most popular, the IEEE 802.3 standard. And they go into such things like token ring, which we talked about last week. Remember the 4 different layouts of a network. You had bus, token ring, star, and hybrid. Because when it started, Ethernet started, networking started in companies. The reason these guys created it, you can imagine, is they're wanting to connect their printers to what in the company? What do they want to connect their printers to? To what in the company, you think? So if you're at your desk and you're sitting there, you're wanting to print something, they're wanting to take that printer, the Xerox printer, and make it to where it's more globally accessible, versus up to that point, every computer physically had a line to a printer, right? Well, if it's on a network, if it's a way to put it on a network, then that solves a problem. And that's why they created this thing we call Ethernet today, that is a backbone of our network. And one of the first topologies was token ring, using coaxial cable. And token ring was developed by IBM, and it relies upon direct links between nodes in the ring. It's nearly obsolete, still around very, very old manufacturing, maybe some research and development and healthcare. Ethernet frames and token rings differ. They won't interact with each other. Devices cannot support more than 1 frame per physical interface. The way token rings work, if you remember last week, it has basically it duplicates the packet as you're sending it to two other devices that it's closest to, and as it goes through the network, it keeps duplicating those to 2 others as it goes across. And so basically, you've got just to being simple here, something like these are data in a ring topology. This is the original computer with sending a 5 meg file. It copies that 5 meg file to the nearest devices once, and say what's going this way. Once it keeps circling around, it eventually X's out, go where it's supposed to go, and verifies it. As you can see, that data is literally copied before it gets to its destination on pretty much every node on the network. So a lot of redundancy, but it made sure that the data was there. And then IEEE Project 802, it basically was built and designed from the Xerox plan on Ethernet to have more error checking, more encryption, or have encryption. It didn't have encryption originally. Different types of network media. They were only first initialized with coaxial cable back then. Wireless didn't exist. Cat5 didn't exist back then. So they had to add some new components to it. Then 802.3 came in to Ethernet. 802.11, wireless was next. And then here's all the standards, all the way down to, I'll mention what you might not have heard of, last two, 802.20 and 22. 802.20 is mobile broadband networking. It's a packet handling specifications for multi-vendor mobile high-speed wireless transmission, nicknamed Mobile WiMAX. This is actually 802.16, which is basically where whole communities offer a Wi-Fi service for entire communities in WiMAX. So this is mobile, just for mobile devices, cellular phones, things like that. Then the last one is called WiRAN. It's regional. It's wireless broadcast network to operate in UHF, VHF frequency. So you remember whenever the TV stations went digital? You guys remember that? Well, when it went digital, those UHF, VHF antennas on the TV stations still exist. They still work. So what they've done since they went digital nationwide is they figured out, let's use that, but now instead of pushing TV channels to locations, we're pushing internet through UHF, VHF. Pretty awesome. And so on the other end, they had to create transmitters and receivers to at the home, a receiver at the home to receive that data like your cable modem, but instead of receiving it via wired on coaxial, it's receiving it wirelessly through antennas through UHF, VHF, and connecting, and you're getting internet connection, which I think is pretty cool. Do I know? Yeah, the 802.22 is the standard, and it's just starting to kind of, there's a few companies specializing in it, not many, but I think if the next big thing, especially in rural areas, places like that, is going to be this WiRAN, because UHF, VHF can travel long distances, like long distances at very low cost, huh? Yeah, using the same exact wave. So instead of having to create something new, they just use existing. And yeah, and so what they're working on now is speeds, because the speeds are, yeah, okay. They're working on getting the speeds up higher, but it's, you know, it's faster than dial-up, faster than DSL, not as fast as high-speed broadband yet, but it's getting there. And so, but again, for places that can't get broadband, which are places that can't get internet through Xfinity, places that can't get satellite, there's places that can't get satellite. It'd be perfect for spots like that, I think, because again, they could have internet where they currently don't have any. So anyway, that's the presentation. But I didn't think you'd heard of 802.11 or 22. That's in my mind, out of all the different 802s, that's the most interesting one to me, because I grew up with UHF, VHF, which maybe it's you and I don't know. So you guys remember UHF, VHF, the TV channel? Okay, you remember a little bit now. When I grew up, we had, it was funny because we had on the TV, instead of the nice outside antenna, we had like I think at one point, in one of the rooms, we had like a coat hanger. It was a coat hanger, was used as an antenna, right? And you had to move it, put aluminum foil on it, hold it just right. And sometimes you'd have to hold it to watch it. And sometimes the kids would be elected to hold it in a certain spot, depending on what was being shown. Yeah, so anyway, it's a whole cultural thing. You had to get up from your chair to actually do it, so you couldn't use a remote. Didn't have a remote. All right, so let's go ahead and watch the video. This is about a 10-minute long, 13-minute long video. Once we're through with this, we are done. When I came in tonight, it was pretty slick on the parking lot, so please be careful. They've not plowed it at all. You guys know that they came in, so just be careful when you leave. Let me pull this up real quick. This was created, Warriors of that was created by a local company years ago to explain the data packets, what we're talking about tonight. It begins on their website. Did you ever wonder how the internet works? How does a router look like? What color does an IP packet have, and how does it travel through a firewall? All these answers and many more can be found on Warriors of the Net movie, and it's all free. So I'm going to go ahead and download this movie. Wi-Fi good enough, probably, I'm guessing. We'll see. I usually download it, but we'll see if it's any good here. Let me Pause it, coming in. Let me, just in case, I don't quite trust that, so I'm going to do the old download here.
That was the trailer though.
Do I?
That was the trailer.
Oh, was that the trailer? That wasn't the full one, was it? Thank you. That was not the full one. Go one in two places.
He came with a message, with a protocol all his own.
Going crazy.
He came to a world of cruel firewalls, uncaring routers, and dangers.
I'll find it. Okay, there we go. All right, don't want the trailer. We redid this. So movie in HD, English. Yeah, I guess that's it. I will copy that link. Okay, yeah, 13 minutes. That's the right one. All right, so let me pause it. And let me download it. I don't trust our connection. Yeah, we'll do that one. That'll work. I don't want the video. MP4. There's 16 meg. It shouldn't take too long. 1 minute, 2 minutes, 3 minutes. It keeps increasing. And while it's doing that, let me I also have it somewhere else. Let's not do it that way. Let's do it this way. Just in case it fails, I think I have it in my Dropbox too. So I got rid of it. Got my other videos, but not that one. Oh well, should be almost done. Wi-Fi. Ooh, it's a slow Wi-Fi. Let's put it on the faster Wi-Fi. Once it paused here, and once it gets connected again. This one here. There we go. Not gonna let me restart it. Okay. One more time. Yeah, that was a slow connection we were on. think this one's a little faster. All right, while that's loading, let me go to their website, show you more. So tons of different versions can be downloaded. They have a new thing they've added here for tools. They've got a subnet calculator they've added to this. It's flash enabled. They have a shop. Guessing in this one, t-shirts for Warriors of the Net. And let's see what else they got. Donate, manuscript. Again, fireside reading if you have nothing to read on the weekend, do that. They made it in the late 90s. Is when this was made. And I'm not canceling it. While it's doing that. I said to get rid of it. Okay. Well, hey, by Sunday it's supposed to be 40 degrees. Right? That's good news.
Jumping from, what was it on Wednesday?
Do I know?
It was jumping from whatever it was on Wednesday, like, what was it, the negative for like in chill.
Yeah, yeah.
That was ridiculous.
Oh, crazy.
All the way up to like 40.
Yeah.
40. No.
Now, does anybody know anybody doing the snow sculpting? Mississippi? They started that yesterday, I guess. They started doing the ice sculpting challenge. Do what now? I think it would, for sure by Sunday, right? I think they just started it. I think they started it yesterday, if I'm not mistaken. They're supposed to be 40, 44, 45 on Sunday. So, yeah. Oh, yeah. I think this morning at 5 o'clock, I was driving on the road. It was negative 23. By 8 o'clock, it was negative 26. And then it started getting warmer, I think, around 9 o'clock in the morning, 8:39. But it kept dropping for, and that was without wind chill. That was like real temperature. So thankfully, the wind wasn't too bad this morning. So it was only like a mile or two. If it would have been higher than that, it'd been, 5 miles an hour, 10 miles an hour, 20 miles an hour would have been pretty bad. It was bad enough already. But do you guys ever try to do the hot water in this weather? Where you get a cup of hot water and throw it? You ever try to do that? Have you ever done it before? Oh, yeah, it's a lot of fun. Yeah, you just basically get a really, really cold cup of hot water or cold of hot water. Not a lot, just about that much at the bottom of the cup, like a coffee cup or something. Just make sure you're not going against the wind. It's not coming towards you. And then when you throw the water out, it turns into ice, like snow, basically, if you throw it up high enough. But it's got to be really hot water. It doesn't only works on hot water, not cold water. So you have to get a chance to do that. Huh? Yeah, I've done it before. I did it actually today when I was at lunchtime. I always have to do it. Why not? It's kind of fun.
How cold is it?
It doesn't have to be this cold. You can start doing it, I think, like once it gets below zero. But I've done it around 5, 10 below. I think you can do it even warmer than that, though. As long as the temperature, as long as the air is below freezing, it should work. Yeah. But again, the water has to be really, really, really hot. It doesn't work with cold water. And it's also, if your water is hard, a lot of hard water, it won't work too well. It's got to be it works really well with like distilled water. Hard water doesn't work too well as either. But it's kind of fun. Remember that from my science teacher years ago. Because Missouri's got quite a bit of ice. We get quite a bit of ice. So a lot of ice storms. Here, not so much, which is good. But Kansas City, Joplin, Springfield, even St. Louis, we get a lot of ice storms where, you can move in snow, but ice, there's really not much you can do. So, not much traction you can get in ice. But what we would do is actually have chains we put on our tires that time of year. Chains with spikes is the only kind of traction you could get. You had to be careful because you had to take them off right when the roads were clear. You had to take them off because they'd really tear up the roads. Spikes would really tear the roads up. All right, according to this, under 10 seconds. We'll see. Oh, it's gonna happen. It's gonna be 10 seconds. All right, cool, yay. All right, now we go. Let's see here. Yeah. We're almost there. 100. Yeah, there you go. Now I feel better. I just know that YouTube one every once in a while get choppy, if I remember right. Let's go full screen.
For the first time in history, people and machinery are working together, realizing a dream. A uniting force that knows no geographical boundaries without regard to race, creed, or color. A new era where communication truly brings people together. This is the dawn of the net. Want to know how it works? Click here to begin your journey into the net. Now, exactly what happened when you clicked on that link? You started a flow of information. This information travels down into your own personal mailroom, where Mr. IP packages it, labels it, and sends it on its way. Each packet is limited in its size. The mailroom must decide how to divide the information and how to package it. Now, the package needs a label containing important information, such as sender's address, receiver's address, and the type of packet it is. Because this particular packet is going out onto the internet, it also gets an address for the proxy server, which has a special function, as we'll see later. The packet is now launched onto your local area network, or LAN. This network is used to connect all the local computers, routers, printers, etc. for information exchange within the physical walls of the building. The LAN is a pretty uncontrolled place, and unfortunately, accidents can happen. The highway of the LAN is packed with all types of information. These are IP packets, no-flow packets, Apple Talk packets. They're going against traffic, as usual. The local router reads the address and, if necessary, lifts the packet onto another network. The router, a symbol of control in a seemingly disorganized world.
Sorry about that. This goes here. This one goes here. I don't like this. Let's go this one. Let's go here. Let's move this one here. Another jam here. Let's put that one here. Let's put that one here.
There he is, systematic, uncaring, methodical, conservative, and sometimes not quite up to speed.
Sorry.
But at least he is exact, for the most part. As the packets leave the router, they make their way into the corporate intranet and head for the router switch. A bit more efficient than the router switch plays fast and loose with IP packets, deftly routing them along their way. A digital pinball wizard, if you will.
Here we go. Here comes another one. And it's another one. One. Hey, Mom. Here goes the whoop. We're on the back. Hey, in there. Over the left, over the right, over the left, over the right. You got it. Here it comes. Right out. He shoots. He scores. It's going. Hey, wait. You watch out. Here comes another one. Oh, here we go.
As packets arrive at their destination, they're picked up by the network interface, ready to be sent to the next level. In this case, the proxy. The proxy is used by many companies as sort of a middleman in order to lessen the load on their internet connection, and for security reasons as well. As you can see, the packets are all of various sizes, depending upon their content. The proxy opens the packet and looks for the web address or URL. Depending upon whether the address is acceptable, the packet is sent on to the internet. There are, however, some addresses which do not meet with the approval of the proxy, that is to say, corporate or management guidelines. These are summarily dealt with. We'll have none of that. For those who make it, it's on the road again. Next up, the firewall. The corporate firewall serves two purposes. It prevents some rather nasty things from the internet from coming into the intranet, and it can also prevent sensitive corporate information from being sent out onto the internet. Once through the firewall, a router picks up the packet and places it onto a much narrower road, or bandwidth, as we say. Obviously, the road is not broad enough to take them all. Now you might wonder what happens to all those packets which don't make it along the way. Well, when Mr. IP doesn't receive an acknowledgement that a packet has been received in due time, he simply sends a replacement packet. We are now ready to enter the world of the internet. A spider web of interconnected networks which span our entire globe. Here, routers and switches establish links between networks. Now, the net is an entirely different environment than you'll find within the protected walls of your lab. Out here, it's the Wild West. Plenty of space, plenty of opportunities, plenty of things to explore and places to go. Thanks to very little control and regulation, new ideas find fertile soil to push the envelope of their possibilities. But because of this freedom, certain dangers also lurk. You'll never know when you'll meet the dreaded ping of death. A special version of a normal request ping, which some idiot thought up to mess up unsuspecting hosts. The paths our packets take may be via satellite, telephone lines, wireless, or even transoceanic cable. They don't always take the fastest or shortest routes possible, but they will get there. Eventually. Maybe that's why it's sometimes called the worldwide wait. But when everything is working smoothly, you can circumvent the globe 5 times over at the drop of a hat. Literally. And all for the cost of a local call or less. Near the end of our destination, we'll find another firewall. Depending upon your perspective as a data packet, the firewall can be a bastion of security or a dreaded adversary. It all depends on which side you're on and what your intentions are. The firewall is designed to let in only those packets that meet its criteria. This firewall is operating on ports 80 and 25. All attempts to enter through other ports are closed for business. Port 25 is used for mail packets, while port 80 is the entrance for packets from the internet to the web server. Inside the firewall, packets are screened more thoroughly. Some packets make it easily through customs, while others look just a bit dubious. Now, the firewall officer is not easily fooled, such as when this ping of death packet tries to disguise itself as a normal ping packet.
It's okay, it's okay. No problem. Have a nice day. Be out of here. Bye.
For those packets lucky enough to make it this far, the journey is almost over. It's just a lineup on the interface to be taken up into the web server. Nowadays, a web server can run on many things, from a mainframe to a webcam to the computer on your desk. Why not your refrigerator? With a proper setup, you can find out if you have the makings for chicken cacciatore or if you have to go shopping. Remember, this is the dawn of the net. Almost anything's possible. One by one, the packets are received, opened, and unpacked. The information they contain, that is, your request for information, is sent on to the web server application. The packet itself is recycled, ready to be used again, and filled with your requested information. Addressed and sent out on its way back to you. Back past the firewall, routers, and on through to the internet. Back through your corporate firewall. And onto your interface. Ready to supply your web browser with the information you requested. That is, this film. Pleased with their efforts and trusting in a better world, our trusty data packets ride off blissfully into the sunset of another day, knowing fully they have served their masters well. Now, isn't that a happy ending?
All right, there you go. Warriors of the net. Warriors of the net. All right. Well, again, made in the late 90s, but still applicable. The networking still the same as it was then as far as how things flow. It's informative, and you probably didn't know the network talked like that whenever packets went across, and now you do. All right. Well, again, be safe when you go home. Went over everything that's due Sunday, and see everybody next week. Awesome. Be careful out there. Enjoy the weather Sunday. It's looking warm up. So just think of that. Think of that. That's all you can do. Oh, do me a favor, shut down your computers around you. That'd be awesome. you can do that, appreciate it.